A perfectly straight line across dozens of miles was once drawn with nothing but chains and compasses. You will discover the forgotten art of how early surveyors mapped entire continents with astonishing accuracy long before satellites existed. How did they maintain a straight line through dense forests where no distant target was visible? What kept their measurements precise across rivers and over mountains without a single modern instrument? Their story reveals a hidden world of geometry and grit that shaped the map you use today. What does it take to impose order on a wild and uncharted land? A surveyor's work began with a single line scratched into the earth. Picture a figure in colonial America standing at the edge of a vast forest with a Gunter's chain in hand. This chain, exactly 66 feet long and composed of 100 links, was his primary tool for imposing order on the wilderness. His first task was to establish a baseline, a perfectly straight and precisely measured line from which all other measurements would originate. This was the foundation of the entire operation, a fragile thread of accuracy stretched across an unpredictable land. The principles he relied on were not new. They were the ancient truths of geometry and trigonometry, known for millennia but now applied with immense practical consequence. As the renowned surveyor Andrew Ellicott wisely noted, the art of surveying depended more upon practice and judgment than upon abstract mathematical knowledge. This baseline was the ultimate test of that judgment. Every link of the chain had to lie flat and true, every measurement meticulously recorded against the pull of a steep hill or the obstruction of a dense thicket. From this single, trusted line, the surveyor could begin the process of triangulation. By measuring the angles from each end of the baseline to a distant, fixed point like a distinctive tree or a rock formation, he could calculate its exact position, creating the first triangle in what would become a vast, invisible web covering the landscape. This method transformed an impassable swamp or a roaring river from an insurmountable barrier into a mere variable in a calculation. But how could they be sure that a measurement taken today would hold its meaning years later, after saplings had grown into trees and streams had changed their courses? The answer lay in anchoring their work to the immutable. They used the fixed stars at night as their guide and chose permanent landmarks that would endure. This careful, deliberate process of creating a reliable foundation from simple geometry was the essential first step, the bedrock upon which the conquest of vast distances was built. The surveyor's chain was more than a tool, it was a system of thought made of metal. Stretched across the land, its 66-foot length and 100 links became a portable standard, a unit of account that could translate wilderness into property. This was the Gunter's chain, the brainchild of Edmund Gunter in the early 17th century. His design was a stroke of practical genius. He did not simply create a measuring stick, he built a calculator. He defined the chain so that 10 square chains equaled exactly 1 acre. This meant a surveyor could measure a line and instantly understand the area of the land he was mapping, weaving calculation directly into the act of measurement. This tool standardized the process across the entire British Empire and its colonies, creating a common language for the land itself. But using this chain was a feat of human coordination. A team would stretch it taut, with assistants holding tall, ranging rods at the far end to keep the line straight by sight alone. Every link had to lie flat, every measurement recorded with precision, because a single error would multiply with every subsequent chain length. Imagine the challenge of crossing a river. They could not simply wade across with a chain sagging in the current. Instead, they used geometry, measuring a baseline along the bank and using triangulation to calculate the distance across the water without ever getting the chain wet. The chain was a literal and figurative link, a testament to how practical innovation and teamwork could impose a grid of order upon the most uncooperative terrain. Direction came from a simple but vital instrument, the surveyor's compass. This device, often called a circumferentor, gave the surveyor his bearing, a fixed line of sight across landscapes that offered no other guide. By aligning the compass needle with magnetic north, he could establish a direction for his chain line, transforming a random path into a documented course. This magnetic north was the directional backbone for the entire survey, the constant reference that oriented every map he would later draw. Yet this tool held a subtle secret known to every experienced practitioner. Magnetic north is not true north, a discrepancy called variation that changes with both location and time. A compass needle might point a few degrees east or west of the actual pole, a small error that could grow into a massive displacement over dozens of miles. To correct for this, surveyors periodically recalibrated their compasses by taking sightings on the stars, using the unchanging heavens to find their fixed point in the world. This practice of cross-checking the magnetic against the celestial was what separated a rough sketch from a precise survey. The compass truly revealed its power in the method known as a traverse survey. Think of it as connecting the dots across an unknown territory. The surveyor would move from point to point, measuring the distance with his chain and recording the direction with his compass for each leg of the journey. By carefully documenting this series of connected lines and angles, he could map a winding river or a meandering boundary with remarkable accuracy. The journals of the Lewis and Clark expedition are filled with such entries, their compass bearings and distance estimates painstakingly recorded day after day, creating the first reliable maps of the American interior. But what happened when the land itself conspired to mislead the compass? Local deposits of iron ore could pull the needle wildly off course, creating perplexing anomalies. A seasoned surveyor learned to detect these deceptions. He would watch for inconsistencies in his readings or take a bearing from a different location to see if the needle settled on a new, contradictory point. By recognizing these invisible forces, he could correct his work, ensuring that his directional backbone remained straight and true. The compass, therefore, was not a blind follower of magnetism, but a tool guided by human judgment and celestial truth, plotting a reliable course through the greatest of unknowns. High on a hilltop, a surveyor peers through his Theodolite, a device far more precise than a simple compass. He is not looking at the path ahead of him, but at two distant peaks on the horizon. His goal is not to measure the miles of rugged terrain between them directly, but to calculate that distance from where he stands. This is the powerful art of triangulation, a geometric method that allowed a handful of men to map entire mountain ranges. The principle is elegant in its simplicity. If you know the exact length of one side of a triangle, and you can measure the two angles from that baseline to a distant point, you can calculate the lengths of the other two sides without ever setting foot on them. That single, trusted baseline becomes a seed from which an entire network of triangles can grow, each new point providing a fresh baseline for the next set of measurements. This method created a vast, invisible web of precision draped over the landscape. The Great Trigonometrical Survey of India used this very approach to measure the subcontinent, painstakingly building a chain of triangles from the southern coast to the mighty Himalayas. Closer to home, the famous Mason-Dixon line, which settled a bitter border dispute, was established through triangulation. Its accuracy was so respected that it became a cultural dividing line in a growing nation. But how did this work in practice, in a place where direct measurement was a physical impossibility? Consider the challenging task of surveying the border between New York and Canada. This region was a labyrinth of dense, unbroken forest and countless lakes. A surveyor could not simply chain his way through such a wilderness. Instead, teams would clear narrow lines of sight through the trees, creating visual corridors to distant signal towers or prominent natural features. From a carefully measured initial baseline, they would take precise angular measurements to these points, solving each new triangle mathematically. Every calculated distance became the foundation for the next triangle, allowing the survey to leapfrog across lakes and over impassable terrain. The entire system, however, depended entirely on the flawless accuracy of that very first baseline. How could they be certain that this foundational measurement was perfect? They treated its measurement with almost ceremonial care. Teams would use specialized rods and temperature-compensated chains, measuring and remeasuring the line on level ground, often taking days to confirm a distance of just a few miles. They knew that a tiny error here would be magnified with every subsequent calculation, potentially throwing a borderline miles off course over a long distance. This meticulous attention to the very first step transformed surveying from a trade of simple chaining into a sophisticated science of angles and calculations, proving that the most powerful tool for mapping a continent was not a chain or a compass, but an understanding of geometry itself. The accuracy of an entire continent's map rested upon a single, fragile line. Before any grand triangulation could begin, surveyors had to measure one baseline distance with near-perfect precision, the one length in the entire network that would never be calculated, only directly and painstakingly measured. For the principal triangulation of Great Britain, they chose the surface of a frozen river, a naturally level and stable plain stretching for miles. Here, they could lay their specialized measuring rods end to end without the constant battle against hills or thick undergrowth. These were not ordinary chains, but instruments calibrated against a national standard, often made from metals chosen for their resistance to temperature changes. Even so, they accounted for everything. On a warm day, a metal rod expands, so surveyors recorded the temperature constantly, applying tiny corrections for the heat of the sun. They used tripods to suspend the chains, eliminating the sag that gravity imposes on a freely hanging line. And they checked for the slightest slope with spirit levels, knowing that a measurement taken along an incline is longer than the true horizontal distance. The process was one of relentless verification. A team would measure the entire baseline, then turn around and measure it again in the opposite direction. Any persistent difference between the two results revealed a hidden systematic error, a flaw in their method or tool that had to be found and eliminated. This act could take weeks for a line only a few miles long, but how could they be sure their trusted chain was still true? They carried a standard measure with them, a reference bar of known, unchangeable length. Before and after each day's work, and often multiple times throughout the day, they would carefully compare their working chains against this physical truth. This ritual of calibration was their anchor to reality. A stretch of even one part in 10,000 might seem insignificant, but over a 5-mile baseline, that tiny error would translate into a miscalculation of over 2.5 feet. And since every subsequent triangle would multiply that initial mistake, a single misstep at the very beginning could displace a mountain on the final map by hundreds of feet. The creation of this baseline was therefore an act of profound humility, a slow and deliberate ritual of verification that formed the unshakable foundation for everything to come. While the compass offered a daily guide, it pointed only to a shifting magnetic pole. For a foundation that would last centuries, surveyors had to look beyond the Earth to the fixed and timeless grid of the stars. On a clear, cold night, a solitary figure might be found bent over a sextant, patiently waiting for Polaris to cross his meridian. This was not a task for haste. By measuring the precise altitude of the North Star above the horizon at the moment of its transit, he could calculate his exact latitude. Each careful observation tied his work on the ground to a cosmic constant, correcting the small but cumulative errors of his magnetic compass. The sun served a similar purpose by day. At local noon, when the sun reached its highest point, its altitude provided another reliable check on latitude. These celestial fixes transformed a local survey from a collection of relative measurements into a node within a global network. For longitude, the challenge was far greater, demanding a precise knowledge of time. Before portable chronometers, surveyors turned to the moon. They used the lunar distance method, measuring the angle between the moon and specific stars. Because the moon moves predictably against the starry background, this angle acted as a clock hand in the sky, revealing the time at a reference meridian like Greenwich. By comparing this celestial time to local solar time, they could calculate their longitude. This was a demanding art, requiring complex tables and steady hands, but it was the only way to anchor a map to the world's true east-west grid from the wilderness. How did they manage such precision with simple field instruments? A quadrant or sextant, though mechanically straightforward, became an extension of the surveyor's own patience and skill. He had to hold the device perfectly level, often braced against a tree or a tripod, his eye carefully aligning the horizon with a reflected star. A single misjudgment in the flickering light could mean an error of miles. Yet, through this painstaking process, the distant and unreachable stars became their most trusted partners. The star charts and astronomical tables they carried were as vital as their chains, allowing them to transfer the perfect, unchangeable geometry of the heavens onto the imperfect, ever-changing earth below. A wide river was not a barrier, it was a geometry problem waiting to be solved. Confronted by a swift current too dangerous to chain across, a surveying party would not be deterred. They would turn to one of the most elegant principles of geometry, the similar triangle. On their side of the river, they would measure a convenient baseline along the bank, a line of known length. Then, from each end of this baseline, they would take careful compass bearings to a single, prominent tree or rock on the opposite shore. With these angles recorded, they would physically construct a smaller, proportional version of the large triangle on their own safe ground. By measuring the corresponding sides of this manageable small triangle, they could use simple ratios to calculate the exact distance across the treacherous water without ever getting a link of their chain wet. This was the power of indirect measurement, turning an impassable obstacle into a solvable equation. Mountains presented a vertical challenge that required a different kind of calculation. To determine the height of a peak and its horizontal distance, surveyors used a method called reciprocal vertical angling. One team would set up a theodolite at a known point and measure the angle to the summit. At the same time, another team at a different, known location would do the same. With these two angles and the measured distance between their two stations, they could solve the triangle in 3 dimensions, pinning down the mountain's exact position and elevation, integrating the very shape of the Earth into their maps. But what about a dense forest where no distant target was visible for days at a time? Here, the surveyor's work became a battle against the immediate environment. Teams had to physically clear narrow avenues through the undergrowth, creating straight lines of sight that were often only a few feet wide. In the deepest woods, where even sightlines failed, they sometimes resorted to sound. A gunshot's sharp report could be used for a rough distance estimate over short spans. By measuring the time between the flash and the sound reaching them, they could approximate the distance to a fellow team member, a crude but effective stopgap in a world of green obscurity. Every single obstacle, from a roaring river to a silent, trackless forest, demanded a unique solution born from a deep understanding of mathematics and a generous dose of raw fieldcraft. The true measure of these early surveyors was not just their precision, but their profound adaptability, their ability to blend the abstract truths of the classroom with the stubborn realities of the wild. The surveyor's world was built on angles, and the instrument that mastered them was the theodolite. While the compass gave a general direction, the theodolite captured angles with surgical precision, becoming the true brain of the triangulation network. Its evolution began with simple sighting tools, but by the 18th century, it had transformed into a masterpiece of mechanical engineering. The key to its accuracy was the vernier scale, a clever sliding attachment that allowed a surveyor to read angles down to a single minute of arc, 1/60th of a degree. This was not just an improvement, it was a revolution in measurement. At the heart of this revolution stood instrument makers like Jesse Ramsden. His great Theodolite, commissioned for the Ordnance Survey of Great Britain, was a legend in its own time. The massive brass circle, 3 feet in diameter, took 3 full years to build and graduate with its delicate, precise markings. This was not a tool for a quick measurement. It was a national investment in accuracy, an instrument so stable and reliable it could define the very shape of a country. In the field, the Theodolite became the surveyor's command center. Set upon a heavy, stable tripod and carefully leveled, it allowed a single person to measure both horizontal and vertical angles from one station. A surveyor could now look through the telescope, sight a distant signal tower on a hilltop miles away, and record the exact angle. Then, with a simple turn of the instrument, he could sight the next station and the next, rapidly building a web of control points without moving from his spot. This process of reading the Theodolite was a careful ritual. The surveyor would look through the main telescope, bring the crosshairs perfectly onto the target, and then read the angle from the finely engraved circles. First the coarse reading from the main scale, then the hyper-precise reading from the vernier. But such precision demanded constant vigilance against deception. The instrument itself could develop subtle errors. Collimation error meant the telescope's line of sight was not perfectly perpendicular to its tilting axis, while axis tilt meant the entire instrument was not perfectly level. To correct for these, the surveyor used a method of repetition. He would take a measurement to a target, then flip the entire telescope over and take the measurement again from the opposite side of the circle. Any difference between the two readings revealed the instrument's hidden flaws, and the true angle was the average of the two. This act of self-correction was fundamental, a way of making the tool confess its own slight imperfections so they could be mathematically eliminated. The Theodolite was more than a collection of brass and glass. It was the pinnacle of pre-industrial engineering. It took the abstract concept of an angle and gave it a number, a precise value that could be recorded in a field book and used to calculate distances to inaccessible places. This single instrument, with its vernier scales and corrective rituals, turned the art of seeing into the science of mapping, proving that the most accurate pictures of our world are not drawn with pens, but constructed from a network of perfectly measured angles. Across the vast emptiness of the American West, a sudden flash of light on a distant mountaintop was more than a signal. It was a lifeline of precision. When survey teams were separated by dozens of miles of desert or sheer mountain ranges, they turned to the sky itself to connect their work. They used signal fires by night and the brilliant flash of the heliograph by day. The heliograph was a marvel of simplicity, a mirror mounted on a tripod that could be tilted to catch the sun and flicker its beam toward a far-off colleague. Under perfect conditions, this controlled spark of sunlight could be seen for over 100 miles, creating a perfect, unmistakable target for a Theodolite's crosshairs. This method transformed isolated hilltops into nodes in a vast, silent communication network. The process demanded immense coordination. Teams had to agree on a schedule, often using astronomical tables to synchronize their watches. They would signal their readiness, then one station would become the active beacon, flashing its mirror in a pre-arranged code while the other teams trained their instruments on the brilliant point of light. But the atmosphere itself was a source of deception. On a hot day, the air near the ground could shimmer, bending the light from the signal and making it appear to dance in a false position. This phenomenon, called atmospheric refraction, was a constant enemy. Surveyors learned to take their sightings in the cooler, more stable air of early morning or late afternoon when the light traveled a truer path. How could they be sure the flash they saw was the right one in a landscape of multiple teams? The coded sequences were essential, a rhythmic blinking that confirmed identity and purpose, turning a simple reflection into a conversation of angles and confirmations. This intricate visual telegraphy, often managed by Army Signal Corps personnel for its discipline, allowed the great geodetic surveys to stitch together a continent one distant sun-fueled flash at a time. Behind every precise measurement and every calculated triangle stood a human team, a small, mobile society forged in the wilderness. A typical surveying party was a masterpiece of organization, with each member performing a specialized role that was critical to the whole. The chief surveyor was the mind of the operation, a figure of immense responsibility who directed the work, guarded the delicate instruments, and performed the complex calculations on the spot. His decisions, made in the face of unexpected obstacles, could determine the success or failure of an entire season's work. Then came the chainmen, the muscle of the enterprise. Their job was deceptively simple: to stretch the 66-foot chain taut and level for every single measurement. But this required immense physical stamina and unwavering attention, as a single sag or misstep would introduce error that could ripple across a continent. Ahead of them worked the axemen, the vanguard who carved order from chaos. With relentless swings, they cleared narrow avenues through dense forests, creating the straight lines of sight without which the Theodolite was blind. Holding the end of each new measurement was the rodman, a statue of patience who kept the tall, ranging rod perfectly vertical and steady, a human landmark in a sea of green. This was not a job for solitary individuals, but for a disciplined, interdependent unit. The famed explorer and surveyor David Thompson wrote extensively of his crews, detailing not just the measurements but the shared hardships, the evenings around a campfire, and the deep camaraderie that made the grueling work possible. They operated for months in absolute remoteness, a self-contained community whose survival depended on mutual trust. But what happened when that community was fractured? If illness or an accident befell a key member in the middle of nowhere, the entire mission could be thrown into jeopardy. There were no substitutes, no quick replacements. The party had to adapt, redistribute tasks, and rely even more heavily on their shared knowledge and resilience. The success of these monumental surveys, the very lines that would define nations, rested as much on this human organization and sheer grit as it did on the technical skill of triangulation. The land was conquered not by instruments alone, but by the disciplined hands and steadfast hearts of the people who carried them. The Mason-Dixon line was far more than a border. It was a masterclass in precision carved directly into the landscape. In the 1760s, astronomers Charles Mason and Jeremiah Dixon arrived in the American colonies with a monumental task: to settle a bitter dispute between the Penn and Calvert families by marking the true parallel of latitude that separated Pennsylvania and Maryland. Their tools were the finest of the age, a state-of-the-art zenith sector for determining their exact position from the stars, and a massive theodolite for controlling direction across the miles. For 5 grueling years, their team pushed westward, crossing the rugged Allegheny Mountains and navigating complex territorial politics, all while maintaining an almost unbelievable accuracy of less than 1 arcminute. How do you ensure a line remains straight when the very ground beneath your feet is curving away? The Earth is not flat, and a line of latitude is a complex curve. To follow it, Mason and Dixon had to constantly adjust their path, using their celestial observations to correct for the planet's spherical shape, ensuring their boundary was a true parallel and not a simple tangent. Their work was made permanently visible through hundreds of boundary markers. Every single mile was marked by a stone brought all the way from England, and every 5th mile was crowned with a more elaborate crown stone, each one a physical testament to the unerring line stretching behind and ahead of them. This stone, placed with such care, is a silent witness to the fusion of astronomical science and sheer human endurance. The line they created would later take on a profound cultural meaning, yet its original legacy is one of technical triumph, a demonstration that with the right tools and unwavering determination, human beings could impose a geometrically perfect order upon a wild and unpredictable continent. The Great Trigonometrical Survey of India stands as a monument to human ambition, a 70-year endeavor to measure a subcontinent with geometry. Beginning under William Lambton and later championed by George Everest, this project was a logistical ballet performed on a nightmarish stage. Its goal was to stretch a chain of immense triangles from the southern coast all the way to the foothills of the Himalayas, creating a precise mathematical skeleton for the map of India. The primary tools for this colossal task were the great Theodolites, instruments of such staggering size and weight that they became characters in the story themselves. Weighing over half a ton and requiring transport by teams of 40 or more men, these were not tools to be carried in a pack. Moving them through dense jungle or across raging rivers was an epic undertaking. How did you transport a delicate, precision-made instrument worth a fortune and critical to the entire mission, on a bamboo stretcher through terrain that could barely support a single file of men? The process was agonizingly slow, a constant battle against the environment where a single slip could mean the destruction of the very instrument upon which everything depended. Beyond the physical strain, the survey teams faced immense personal hardship. The tropical climate brought with it significant health challenges, with illnesses posing a constant threat to the workforce. The terrain itself was a relentless adversary, from the sweltering, insect-filled lowlands to the thin, cold air of the high mountains. Yet the scientific payoff was worth every ounce of struggle. This survey was not merely about drawing lines on a map. It was a foundational project in the science of geodesy, the study of the Earth's shape and size. By carefully measuring the arc of the meridian across India, the survey provided some of the most accurate data yet collected on the planet's true form, revealing it to be an oblate spheroid, slightly flattened at the poles. The precision of their angular measurements was so extraordinary that when they eventually sighted a distant Himalayan peak known as Peak 15, they were able to calculate its height with stunning accuracy, later naming it Mount Everest in honor of the survey's relentless leader. This project represents the absolute zenith of what was possible before the electronic age, a testament to how sheer human endurance, organized on a massive scale, could coax impossible precision from the most unforgiving landscapes. Even the clearest line of sight was a subtle deception. The air itself, a shimmering lens between the surveyor's theodolite and his distant target, bent the light passing through it. This phenomenon, atmospheric refraction, made objects appear slightly higher than they truly were, a constant, invisible force pulling every measurement astray. The effect was most pronounced on long, flat plains or over stretches of water, where the line of sight grazed the earth for miles. A seasoned surveyor knew that an uncorrected sighting across a calm bay or a vast prairie could introduce an error large enough to misplace a mountain's summit by hundreds of feet on his final map. This was not a flaw in his instrument, but a fundamental property of the world he was trying to measure. How could he possibly account for an error he could not see directly, one that changed with the daily weather? He learned to read the air itself. On a hot, still day, the heat radiating from the ground made the distant target dance and waver in his telescope, a visible warning of severe refraction. He came to prefer the stable, cool air of dawn or dusk for his most critical observations, when the light traveled a straighter, truer path. Through decades of accumulated experience, these practitioners developed empirical rules of thumb. They might consistently subtract a certain number of seconds of arc from a low-angle observation, a correction born not from complex theory, but from the hard-won knowledge of what made their final calculations align. Later, these rules evolved into more formal mathematical formulas that incorporated temperature and barometric pressure, crude but effective attempts to quantify the atmosphere's invisible influence. For a coastal survey determining the height of a lighthouse or a geodetic team measuring the altitude of a far-off peak, mastering this correction was everything. It meant learning to see not just the target, but the entire column of air between them, interpreting its hidden distortions to find the geometric truth beneath. This environmental intuition, this ability to subtract the atmosphere's lie from the telescope's truth, was the final advanced skill that separated a master surveyor from a mere technician. The true map of a continent was not drawn in ink but in numbers. Inside a surveyor's field book, the sweep of a landscape was reduced to neat columns of angles and distances, a cryptic ledger waiting to be decoded. The instrument that unlocked this code was not made of brass or glass, but of paper and ink, the book of logarithmic tables. Before a single coordinate could be plotted, the surveyor faced a mountain of multiplication and division, calculations with numbers stretching to 10 digits or more. A single distance from a triangulation observation, the calculation of a side from a known baseline and two measured angles, could involve multiplying and dividing these enormous figures repeatedly. Doing this by hand was not just slow, it was a minefield of potential error where one misplaced digit could throw a boundary line miles off course. The logarithm was a mathematical superpower, a brilliant shortcut invented in the 17th century. It transformed the exhausting process of multiplication into the simple act of addition, and division into subtraction. To multiply two large numbers, the surveyor would simply look up their logarithms in the tables, add those logarithms together, and then find the number whose logarithm matched that sum. It was a form of calculation so revolutionary it felt like magic, compressing hours of labor into minutes. But this magic demanded absolute precision. The surveyor, or often a dedicated person called a computer, would work by lamplight, his finger tracing down the narrow columns of the logarithmic tome. He would find the logarithm for his measured angle sine, then for the known distance, add them carefully, and then consult a different part of the table to find the anti-logarithm, the final result. Every step was recorded in the field book, the scratch of his pen the only sound marking the birth of a new coordinate. This was a discipline of the mind as rigorous as any physical measurement in the field. What happened when a calculation error was discovered weeks later, long after the team had moved on? There were no digital backups, no undo commands. The entire chain of reasoning for that section of the map had to be painstakingly retraced, number by number, through the pages of the field book until the rogue digit was found and corrected. The pressure was immense, for these numbers were not abstract. They were the future boundaries of farms, towns, and states. The intellectual stamina required for this work, the ability to maintain flawless focus through hundreds of repetitive calculations, was the invisible engine of the entire operation. The Theodolite captured the angles and the chain measured the baseline, but it was the humble logarithm that translated their raw data into a lasting picture of the world. A surveyor's final act was to leave a permanent mark on the world, a physical promise carved in stone or driven deep into the soil. This monument was the ultimate purpose of all the careful chaining and celestial observation, transforming abstract numbers into an unshakable reality on the ground. Whether it was a simple wooden stake for a farm boundary or an intricately carved stone obelisk marking a critical geodetic station, this object held the legal and spatial truth of the land. Its permanence was not just a matter of convenience, it was the bedrock of property rights and future development. A family's claim to their homestead, the border between two states, all of it depended on the enduring presence of this silent sentinel. But how could a surveyor in 1800 be certain that his marker would be found a century later, after forests had fallen and new towns had risen? He did not rely on the monument alone. His field notes contained a precise verbal map, a set of directions to the marker from permanent natural features. He would record the exact bearing and distance to a specific large oak tree, a distinctive outcropping of granite, or the center of a stream confluence. This created a recoverable network of clues, ensuring that even if the original stone was plowed up or the post rotted away, its location could be mathematically resurrected by a future surveyor following the same instructions. These descriptions were copied onto official plat maps, which became the legal DNA of the landscape. The monument itself was only half of the system. The other half was this carefully crafted recovery plan, a set of breadcrumbs left for the future. This practice reveals a profound faith in both the permanence of the natural world and the continuity of human knowledge. The surveyor was not just working for the present, he was speaking directly to his successors, trusting that they would understand his methods and honor his measurements. That stone buried deep in the earth was more than a marker. It was a handshake across time, a fixed point of certainty in a world of constant change. A surveyor's pocket watch was a heartbeat of uncertainty in the vast silence of the wilderness. Before the telegraph could send a unified pulse of time across a continent, every team operated on its own slightly flawed rhythm. A high-quality marine chronometer was a masterpiece of craftsmanship, but it was also a deeply temperamental instrument. Changes in temperature could slow its delicate balance spring or speed it up, while the jolts and jars of travel over rutted trails could subtly alter its rate, the steady gain or loss of seconds each day. For any measurement requiring two distant teams to act at the same precise moment, this was a fundamental problem. How could you trust a critical observation when your partner's reference clock, miles away, might be telling a different story? This limitation forced a profound pragmatism in their methods. Surveyors overwhelmingly favored the beautiful self-containment of triangulation, where angles were measured relative to a fixed baseline and no absolute synchronization was needed. But for anchoring their entire map to the globe, for finding true longitude, precise time was non-negotiable. The solution was to turn to the sky for a shared starting pistol. If both parties could observe the same predictable celestial event, like the sudden disappearance of a star behind the moon, that moment became a universal timestamp. They would each note the exact time on their own watches when the star winked out, and from that shared instant they could calibrate their separate timelines. Transporting these delicate timekeepers was an exercise in constant anxiety. A chronometer might be swaddled in wool and carried in a padded box, suspended in gimbals to keep it level even on a tilting packhorse. The instrument was so vital that its caretaker would monitor its temperature, wind it at the same time each day with a consistent number of turns, and keep a meticulous log of its performance against the stars. Even with this care, they knew the time they carried was only an approximation. The brilliant workaround was to design surveys that depended not on synchronized seconds, but on timeless geometry, proving that the greatest innovations were often not in conquering limitations, but in skillfully dancing around them. Centuries before Gunter's chain, Roman surveyors were imposing their own geometric order across Europe. These agrimensors, the measurers of the land, were the master architects of the straight line. Their most iconic tool was the Groma, a deceptively simple instrument consisting of a vertical staff with a crossarm from which plumb bobs were suspended. By sighting across the hanging weights, a surveyor could establish a perfect right angle, the foundational element for their entire world. With this, they laid out the legendary straight roads that shot across hills and valleys, and the precise grid patterns of their military camps, creating standardized fortifications from Britain to Syria. For leveling, they used the chorobates, a long wooden bench with a water channel carved along its top. When the water rested evenly between marks at each end, the device was perfectly level, allowing them to engineer aqueducts that carried water for miles on a gentle, unerring slope. This was not abstract mathematics, it was geometry made brutally practical. Their most enduring legacy on the landscape was centuriation, the division of conquered territory into vast square grids. Each centuria was a block of land measuring 20 by 20 acres, approximately 200 jugera, forming a colossal checkerboard visible from the air even today in parts of Italy and France. This system prioritized geometric purity over the natural lay of the land, creating a durable and easily administered infrastructure that stamped Roman authority onto the very soil. How did this sophisticated knowledge survive the empire's collapse? The techniques were preserved in manuscripts, studied in medieval monasteries, and rediscovered by Renaissance humanists who saw in the agrimensors a model of rational order. They proved that long-distance alignment was not a question of advanced technology, but of unwavering discipline and a profound belief in the straight line, a precedent that would guide surveyors for the next 2,000 years. The relentless pressure of a single mistake could unravel an entire season's work, a psychological weight carried by every surveyor in the field. This profession demanded more than technical skill. It required a mind specially forged for endurance and microscopic attention. Picture a person who could spend an entire morning perfecting the level of a Theodolite, only to spend the afternoon wading through a swamp, all while maintaining the mental clarity to perform complex logarithmic calculations by firelight. They needed the patience of a cartographer illuminating a manuscript, the resilience of a mountaineer, and the unshakable integrity of a magistrate, for their word, once recorded in the field book, became legal fact. In profound isolation, with no superior to consult, they had to trust their own judgment completely. A decision about whether to accept a slightly shaky compass reading or to redo a week's measurements rested solely on their conscience. This immense self-reliance existed alongside the constant demand of leadership. They had to manage a team of chainmen and axemen, mediating disputes and maintaining morale through weeks of monotonous labor and sudden emergencies. Their personal journals often reveal this inner world, not just as dry records of data, but as reflections filled with a deep fascination for the land itself. What kept a person focused through such hardship was often a profound sense of purpose, a belief that they were imposing a lasting order on chaos, and a quiet appreciation for the stark beauty of a mountain silhouette or a perfectly straight line cutting through an untouched forest. This unique blend of artistic sensibility and scientific rigor turned a technical profession into a calling, where the greatest instrument was not the Theodolite, but the disciplined and resilient human mind behind it. The surveyor's field book, filled with numbers and sketches, was a world waiting to be born on paper. This transformation happened not in the wilderness, but in the quiet confines of a cartographer's workshop. Here, a draftsman would begin with a massive, blank sheet, carefully plotting the precise coordinates calculated from the surveyor's angles and baselines. Each calculated point was a tiny pinprick of certainty, a dot representing a hilltop, a river bend, or a boundary marker. With a steady hand and a sharp pen, he would then connect these dots, drawing the clean, straight lines of the triangulation network. This was the map's invisible skeleton, the mathematical truth upon which everything else would be built. Onto this framework, the cartographer would then pour the soul of the landscape, translating the surveyor's field notes into rich, visual detail. He would add the serpentine curve of a river from a chain of traverse measurements, or sketch the hachured slopes of a mountain from vertical angle observations. This required a delicate art known as generalization, knowing what to include and what to omit for the sake of clarity. A babbling brook noted in the field might become a single, thin blue line, while a vast, impenetrable swamp could be reduced to a stylized symbol. The cartographer's choices in symbolization and elegant lettering determined whether the final map was merely functional or a thing of genuine beauty and intuitive use. This entire process was a profound collaboration between two different kinds of expertise. The surveyor in the field understood the ground truth, the feel of the mud and the scent of the pines. The cartographer at the table understood graphic communication, how to make that complex truth legible and useful to a governor, a settler, or an explorer. But what happened when their worlds collided in disagreement? When the notes from one survey party did not perfectly align with the data from another, or when a new measurement contradicted an old, trusted map? Resolving these discrepancies was a careful exercise in judgment. The cartographer would become a detective, comparing dates, assessing the methods used, and weighing the reputation of the surveyors involved. Often, the most recent and meticulously documented data took precedence, but sometimes a compromise was drawn, a best estimate that acknowledged the imperfections of the craft. The final published map was therefore more than a record. It was a tool that shaped destiny. It guided the routes of wagon trains, decided the location of new towns, and settled legal disputes over vast estates. It was the ultimate purpose of all that grueling fieldwork, a polished window into a newly ordered world, ready to guide the hands of those who would build upon it. The straight lines of the surveyor's map were often traced over pathways known for generations. While the Theodolite captured angles and the chain measured distance, another form of intelligence was essential for navigating the land itself. Indigenous guides possessed a deep, accumulated knowledge of the terrain, a mental map built from a lifetime of observation and the shared wisdom of their communities. They knew which mountain passes remained open in winter, where the safest river fords could be found, and which ridges offered the clearest lines of sight. This was a form of surveying in its own right, a practical geography written not in field books but in memory and story. For expeditions mapping the vast Canadian wilderness or the American West, this guidance was not just helpful, it was a matter of survival. A native guide could distinguish between a seasonal stream and a permanent water source, preventing a party from perishing of thirst. They could identify edible plants and warn of potential hazards, turning an impossible journey into a manageable route. The famed Lewis and Clark expedition, for all its scientific instruments, would have likely failed without the critical assistance of Sacagawea, whose knowledge and presence were invaluable. Yet the exchange of this vital information was rarely simple. Cultural and language barriers created a complex filter through which all geographical knowledge had to pass. A guide might describe a distance in terms of days traveled, a unit that varied with the season and the composition of the party. Concepts like private property or a straight-line border were often foreign to worldviews that understood land in terms of use and relationship. Communication depended on a fragile chain of gesture, pidgin languages, and the skill of interpreters, where a single misunderstanding could lead a survey team into a box canyon or a dead-end swamp. The most successful surveys were therefore hybrid achievements. They combined the precise angular measurements of European instruments with the profound, time-tested wisdom of the people who knew the land intimately. This collaboration, though frequently uncredited in official reports, wove local intelligence directly into the grid of the modern map, a silent testament to a partnership of necessity in the face of the unknown. The relentless pursuit of a straighter line transformed surveying from a rough art into an exact science over generations. The Roman Groma, for all its elegant simplicity, might misplace a line by several feet over the course of a single mile. This was perfectly adequate for laying out a military camp or a local road, but it was a scale of error that would become unacceptable for mapping a nation. The journey from that level of precision to the sub-foot accuracy achieved by a 19th century Theodolite over the same distance is a story of incremental genius. It was not one single breakthrough, but a cascade of improvements in how we see, measure, and think. The first great leap was the invention of the telescope. When it was mounted on a surveyor's instrument in the 17th century, it did not just make distant objects appear closer, it extended the very reach of human sight. A surveyor could now aim his crosshairs at a target miles away with a clarity the naked eye could never match. This immediately reduced the angular errors that had plagued sightings with simple sighting vanes. Then came the vernier scale, a clever sliding attachment that allowed a reader to interpret the finely graduated circles of a theodolite with breathtaking fineness. Where an earlier surveyor might have been able to read an angle only to the nearest tenth of a degree, the vernier allowed readings down to a single minute, 1/60th of a degree. This was a revolution in resolution, but better tools also demanded a better understanding of their flaws. The repeating circle, championed in France, addressed this directly. Instead of taking a single measurement, this instrument allowed a surveyor to accumulate an angle by repeating the measurement multiple times around the circle. The mechanical process averaged out the small, inherent imperfections in the instrument's gears and bearings, yielding a final value far more reliable than any single reading could provide. This marked a philosophical shift, a move from trusting a single observation to trusting a statistical process of self-correction. The demands of massive national projects like the principal triangulation of Great Britain or the Survey of India drove this evolution relentlessly. These enterprises required consistency over hundreds of miles, forcing surveyors to become masters of error. They developed rigorous routines for calibrating their chains against standard measures, and they created mathematical formulas to subtract the distorting effects of temperature on their metal rods and of atmospheric refraction on their lines of sight. Each source of uncertainty was identified, studied, and systematically minimized. So what was the single most important innovation? It was likely the fusion of the telescope with the finely divided circle, a marriage of optical power and mechanical resolution that gave surveyors the ability to see and measure angles with a previously unimaginable fidelity. This core advancement, refined over 2 centuries, turned the theodolite into the undisputed king of instruments. The history of surveying precision is, in the end, a mirror of our growing ability to impose order on the physical world, one carefully measured arcsecond at a time. A perfectly straight line was also a powerful economic engine. Behind every great survey lay a simple, driving question: who owns what? Governments and private investors poured immense fortunes into these grueling expeditions because the answer directly translated into revenue and control. An accurate map made territory legible, transforming uncharted wilderness into taxable property, sellable lots, and defensible borders. This was the practical power of the grid. It created a system of ownership from a state of nature. The monumental Louisiana Purchase offers a perfect example. After the United States acquired that vast territory, the government launched an unprecedented surveying project to plat the land into neat, saleable townships. Each 6-mile square township was further subdivided into 36 sections of 1 square mile each, creating a predictable and marketable grid that fueled westward expansion and filled the national treasury. This geometric order was not just for convenience, it was a deliberate tool for settling the continent. North of the border, a similar story unfolded with the Dominion Land Survey. This project imposed a colossal grid across the Canadian prairies, a pattern of range and township lines so vast it still defines the landscape from the air today. Its primary purpose was to encourage homesteading, to systematically transfer land from the public domain to private hands, and build a stable agricultural economy. The surveyors who laid down these lines were not merely technicians, they were the advance agents of national policy. Their work directly answered the demands of a land grant system or a mining rush, often prioritizing speed and standardization over perfect topographical detail. A survey for a railroad grant, for instance, focused on defining a long, narrow corridor of land, while a mining survey cared most about plotting mineral claims with legal precision. The specific economic drivers shaped the very nature of the map that was produced. So when you look at an old plat map with its clean lines and right angles, you are not just looking at a record of measurement. You are seeing the blueprint of an economy, the geometric expression of political will, and the quiet machinery that turned wilderness into a modern state. The perfectly straight lines of legend were, in reality, a tapestry of meticulous estimations. Early surveyors achieved wonders, but they were not infallible. Their lines were a sequence of the best possible approximations, each one a small victory over difficult terrain and imperfect tools. Over dozens of miles, tiny, unavoidable errors would accumulate, causing a boundary to wander by a few feet or even more. This was not a failure of skill, but a simple truth of physics and human endurance. The myth of lost, secret knowledge is equally misleading. These men were not wizards guarding arcane secrets. Their methods were grounded entirely in publicly available mathematics and physics, their field books filled with the same trigonometry taught in classrooms today. They were brilliant practitioners, not magicians, and their true genius lay in applying textbook principles under the most demanding field conditions. We can see this friction between ideal and reality in the property disputes of early New England. When two separately surveyed plots met, their boundaries often failed to align perfectly, creating slivers of contested land. These discrepancies were not evidence of negligence, but of the craft's inherent limitations. The legal system had to develop pragmatic solutions for these inevitable imperfections. Courts would often uphold the original surveyor's marked corners and blazed trees as the true intent of the boundary, even if the mathematical line drawn later suggested a slight error. This principle, known as acquiescence, recognized that the marked ground truth often held more legal weight than a perfect, abstract calculation. It was a system designed to respect the monumental effort of the original work, while acknowledging the practical reality that no measurement is ever truly perfect. Understanding these historical disputes does not diminish the surveyor's accomplishments. It elevates them. By setting aside the romanticized legend of flawless precision, we can better appreciate their true achievement, which was not mythical perfection, but a hard-won, practical accuracy that was good enough to build a nation upon. Yet for all their ingenuity, the reign of the chain and Theodolite could not last forever. A quiet revolution began in the late 19th century, not with a bang, but with the uncoiling of a steel tape. This simple innovation was the first sign of a new era. Unlike the heavy, link-by-link procession of the Gunter's chain, a steel tape could be laid out in one continuous, swift motion. It was less affected by temperature and sag, offering an immediate leap in both speed and accuracy for direct measurements. Soon after came the precise level, an instrument with a telescope and a highly sensitive spirit level that could establish a horizontal line of sight with near perfection. This allowed surveyors to determine elevation changes with a precision that earlier methods could only dream of, revolutionizing the engineering of canals, railways, and city infrastructures. The most profound change, however, arrived with the birth of electronic distance measurement. These devices, emerging in the mid-20th century, used beams of light or radio waves to calculate distance. Suddenly, a task that once took a team of chainmen an entire day could be accomplished by one person in minutes, with an error margin measured in millimeters instead of feet. The telerometer, which used microwave signals, could even measure distances of dozens of miles through fog and rain, rendering the arduous process of building a chain of triangles across impassable terrain almost obsolete. The final step in this transition was the global positioning system, which effectively moved the reference points from hilltop signal towers to a constellation of satellites. The surveyor's age-old struggle to see from one point to another was over. What was the last major project to rely on the classic methods? Many point to the extensive retracement surveys of the American West conducted through the mid-20th century, where crews used the old tools to find and verify the original public land survey corners. After that, the torch had clearly been passed. This was not an abrupt end, but a gradual sunset for a craft that had defined mapping for centuries. The steel tape and the theodolite did not vanish. but they were no longer the undisputed masters of the field. The principles they embodied, however, proved immortal. The conceptual framework of triangulation, the rigorous discipline of error analysis, and the legal importance of permanent monumentation did not become obsolete. They simply found a new home, becoming the unshakable conceptual foundation for the digital science of modern geodesy. The story of early surveying is a completed chapter, a testament to a time when human skill and simple geometry could measure a continent, and its lessons are permanently inscribed not just on the land, but in the very logic of how we understand our world today. Their story is a quiet monument to what the human mind can accomplish with little more than geometry and grit. From the first measured chain stretched across a forest clearing to the sprawling triangulation networks that mapped entire continents, these pioneers transformed abstract mathematical truths into the very foundations of our modern world. They built the invisible grid of civilization without a single microchip or satellite, proving that careful observation and unwavering dedication can conquer even the most daunting physical limits. Their true legacy is not merely the boundaries they drew, but a powerful reminder that rigorous method and intellectual courage can achieve the seemingly impossible. So the next time you travel a straight road or notice the clean line of a property fence, see it for what it truly is, a silent testament to a forgotten art of measurement. We would love to hear which of these historical techniques surprised you the most. Share your thoughts in the comments and subscribe for more journeys into the hidden engineering of our past.